Hello, y'all, and welcome back to the DP Chemistry curriculum. We are on lesson 10, structure 1.3.6. This is an HL lesson, as will be the next one. In this lesson, we're going to be covering the limit of convergence at higher frequencies and how that corresponds to ionization. We will be able to explain the trends and discontinuities in first ionization energy across a period and down a group. We'll be able to calculate the value of the first ionization energy from spectral data that gives us wavelength or frequency of the convergence limit. We're going to be using some stuff such as the value of Planck constant and the equation E equals HF and C equals lambda F. And those are all within the data booklet, so you will not need to memorize them, just know how to use them. So as we move into our lesson, describing and calculating ionization energy, the first thing we got to do is talk about atoms and specifically what holds the atom together. When we look at atoms, they're made of two things. Well, three things, but two that we care about. Protons, which are positive, and electrons, which are negative. And as we look at these two, we think about what's called electrostatic interactions. Electrostatic interactions. Electrostatic interactions is basically the interactions between two particles. So a positive particle and a positive particle, a positive particle and a negative particle, or a negative particle and a negative particle. And I'll just make a little key right here. This will be negative particle and positive particle. Now, electrostatic interactions basically say that two things of the same charge will repel each other, two things of opposite charge will attract, and that once again, same charge repel. So atoms are made of positive and negative particles, which therefore fall under electrostatic interactions, and they have these forces that are constantly affecting them. So if we look at the nucleus is just protons and neutrons. According to electrostatic interactions, all these little protons together, along with a couple neutrons in there, would want to repel each other and break apart. Now, the neutrons help buffer that a little by putting space between the particles, but not enough to hold that thing together. So within the nucleus, we have the strong nuclear force that kind of just holds it all together, holds nucleus together. You don't need to know much past that for the DP curriculum, just that the strong nuclear force is what holds it together. Now, the other thing is a little more obvious. Well, how do electrons stay onto an atom? Well, if we look at an atom, we see that electrons are attracted to the positive nucleus. And that is due to our static interactions. And you can kind of think about it like maybe how our planet, Earth, revolves around the sun. The Earth is attracted, it has momentum pushing it forward, and so it kind of makes that revolution. Electrons feel kind of the same forces where they're attracted to the nucleus and they want to go in, but they have so much energy they go around in these weird patterns. And hey, look, we've drawn an atom, kind of. It's a bit more complicated, and by a bit, I mean a lot more complicated than that when we get into quantum mechanics, but we're not going to go that far. We just have to know that electrostatic interactions hold our negative electrons to the positive nucleus. So with that, we have to figure out, well, what can happen based on these interactions? Well, first off, the attraction of electrons can be overcome by application of energy. Basically, if we get an electron and we give it so much energy, it can break free of the nucleus. It can break free of that attractive force. There is a term for this. The energy required for an electron to overcome the electrostatic static interactions is called ionization energy. I will be shortening that to capital I, capital E. So it is called our ionization energy. Alrighty. So let's define ionization really quickly, and I'll switch to a different color. Ionization is the term where so that's where an electron is removed from its atom. Specifically, we're talking about from ground state to n equals infinity. We talked about this when we were talking about the hydrogen atom. So if we look at hydrogen and we have our energy levels again, and I'm just going to do a very rough sketch this time. N equals 1, n equals 2, n equals 3, n equals 4, n equals 5. And that last one I'll actually put pretty close to n equals 5. Make it a little thicker. This is n equals infinity. When we take our electron and we promote it to n equals infinity, we say it is ionized because that's where the nucleus stops having that attractive pull on it or stops having a meaningful pull. The pull becomes negligible. So we have to go back to electrostatic interactions real quick. Electrostatic static interactions. These are based on two things. So you can generally think about electrostatic interactions as like maybe two magnets together, north, south, north, south, and they have this attractive force. And when you think about two magnets coming together and you feel that pull of them attracting, or maybe you flipped it and they're repelling each other because you have north, north, or south, south, you generally start feeling a stronger force when they're closer together. If we bring these magnets closer together, the force is stronger. And if we bring them further apart, the force is weaker. So the first thing that affects this is the distance between particles. In an atom, if you're looking at the nucleus and outermost electron or outer electrons, we call that distance the atomic radius. The other thing that could change it is if you take your magnet and you add a second magnet, north, south, this magnet right here now feels double that force. So you've increased the magnetic pull from one side. So for that, we say the size of the charge or size of, not size, that is the wrong word. I'd like to say magnitude of charge, of charge. Now with atoms, we're talking about the number of protons in the nucleus. And we're talking about the number of protons in the nucleus, we call that the nuclear charge. What we're trying to say is a nucleus with like 5 protons. Oop, one my laser pointer. A nucleus with like 5 protons will pull a lot stronger than a nucleus with 1 proton. So this number of protons will have a greater effect on that charge. All right. So with this said, now we can start looking at ionization energy as a whole, now that we can figure out what's going to affect it. So the first thing I want to do is show you what ionization energy looks like as a trend on the periodic table. So let's look at trends in ionization energy. So I've gone ahead and readied an image from Cognity, and I constantly forget that it assumes I'm trying to write an apostrophe. And in this image, we can see a couple of things. First, it's talking about first ionization energy. All that means at this point is that you're removing one electron, the first electron from that atom. You'll notice between hydrogen and helium, it is harder to remove an electron from helium. You can try and start figuring out why that might be. Helium has 2 protons, while hydrogen has 1 proton. So it should take about double the force, and it kind of does. It takes about 1,200, it takes about 2,400. So it's about double the force to remove it. But then you'll notice that ionization energy goes much further down when we're talking about lithium. And then it goes up to beryllium, down to boron, up, up, down, up, and then it goes big down again, then up, down, up, and so on. What you'll notice, if I'm very careful about this, we'll see if I can get it done. I don't know why this isn't writing. So I'm going to trace that right now. Maybe this won't work. No, I guess it won't. Let's send this to the back. I don't. Anyways, if we trace these two shapes, oh, there it is. You'll notice they're very similar between elements 3 and 10 and between 11 and 18. So with that said, let's ask a couple questions. Number one, what overall trend do we see from 3 to 10 and from 11 to 18? Well, we just kind of described that one a little bit. We see an overall increase. Overall increase. And so we might ask, well, why is that? Why does ionization increase between 3 and 10 and 11 and 18? Well, we can explain that one quite simply. Once we bring up our periodic table, looking for that one again. If we look at our periodic table, we'll notice that between elements 3 and 10, they're all on the same energy level, n equals 2. So electrons are not moving further away from the atom. All that's happening is we are increasing our nuclear charge. So as our nuclear charge increases, that attractive force is stronger. And as that attractive force is stronger, the ionization energy, the energy required to remove that electron, increases. We see that same trend as we look at elements in period 3. N equals 3, we notice that they are all on the same energy level once again, and we are adding protons, meaning our nuclear charge is increasing. And because our nuclear charge is increasing, our atomic radius is staying, sorry, because our nuclear charge is increasing, the energy required to remove each electron gets higher and higher. You'll notice we have a giant decrease between neon and sodium. So between neon and sodium, we have a big decrease. Well, that's because we're going from n equals 2 to n equals 3 energy level. So if we go back to our hydrogen further up here, our elements are going from an energy level close to an energy level further. And we said the distance between particles. It's kind of like moving that magnet further away. If you move the magnet further away, it becomes easier to separate them. So this is why this section gets that decrease. All right. So our second question is, as such, are there discontinuities in the overall trends? So let's once again pull up our image. And as we look at our image, while we notice our trend is overall increasing, we have this discontinuity here and discontinuity here between our second and third element and between our uh, fifth and sixth element. Again, between our second and third element, between our fifth and sixth element. So we have the same discontinuities for both n equals 2 and n equals 3. So on n equals 2, we see there's a discontinuity between beryllium and boron. For n equals 3, that same discontinuity is between magnesium and aluminum. For n equals 2, we have our discontinuity between nitrogen and oxygen. And for n equals 3, it's between phosphorus and sulfur. So we have two discontinuities that are replicated within each energy level. So why might this be? To learn that, we have to look at our electron configurations. So let's start with beryllium and boron. I don't know why I'm writing boron. Let's look at beryllium and boron. Beryllium has the electron config, and I'm going to use my periodic table here. 1s2, 1s2, 2s2. So beryllium is 1s2, 2s2. Boron starts the same way, 1s2, 2s2, but you'll notice it moves over into our p block, and we have 2p1. So you need to make sure you understand our previous lesson on electron configurations to understand this, but here are our electron configurations. Now we're going to use an energy level diagram to describe these. Energy. I'm going to write boron or beryllium in purple, beryllium, and I'll do boron in blue, and I'll put them next to each other. And so what we're doing is our orbital diagrams. Again, this is from our last lesson. And we're going to fill in our electrons. Following the three rules, the Aufbau, Hund, and Pauli exclusion principle, we can fill in our electrons, starting with lowest energy, then going up. Now you'll notice boron actually jumps up to the 2p. So if I label these, this is 1s, 2s, 1s, 2s, 2p. We see that boron puts its newest electron in the 2p orbital. So while boron does have more protons, it has 5 electrons and 5 protons to beryllium's 4 electrons, or 4 protons, 5 protons. We also notice that its most recent electron is in a higher sublevel, meaning it's further away from the nucleus. And once again, we get to that distance. It's like you're pulling your magnet further away. This electron is easier to remove. The p orbitals are further from the nucleus and thus easier to remove electrons from. We can take this same logic and apply to magnesium and aluminum. The only difference is magnesium is 3s2 and aluminum is 3s2, 3p1. And so it's going to be the same diagram, but in the n equals 3 main energy level. All right, moving forward to the second discrepancy. So for the discrepancy between nitrogen and oxygen, as well as phosphorus and sulfur. So let's just go ahead and look. Oh, all right, so we covered beryllium and boron and magnesium and aluminum. Now we're looking at these discrepancies right here. So for those discrepancies, how do we remedy this? Well, guess what? We're going to look at the energy level diagrams again. So nitrogen has 1s2, 2s2, 2p3. Oxygen has 1s2, 2s2, 2p4. So it does have one more proton, but also has one more electron. When we look at the p orbital specifically of these atoms, so this is the 2p, 2p, and we'll say this is nitrogen, and this is oxygen. Following our rules, nitrogen has three, one, two, three. We fill them all with one first. Oxygen has four, one, two, three, and four. So what we notice is that nitrogen only has one electron per orbital, while oxygen has two electrons in one of the p orbitals, with one electron in the other two. So what does that mean for it? Well, we have to go back to electrostatic interactions and notice that electrons tend to repel each other. So the electron in this orbital is repelling the other electron within its orbital. So to write that out, in nitrogen, each orbital has one electron, while, and I should put a one line there, while in oxygen, one orbital has two electrons. These electrons repel each other, another, and therefore they make it easier to remove one of them. So the electrons are actually allowing, within oxygen, that new electron is allowing it to be removed easier because it repels the old electron that was there in the nitrogen configuration. Same thing, once again, between phosphorus and sulfur. So we'll say this applies to phosphorus and sulfur, but we will look at 3p sublevel. All right. So that helps us understand ionization energy, but the other part of this lesson was calculating ionization energy. It seems like a difficult task, but all it takes is a little bit of algebra and some equations that are given to you. So we'll put a little line and say calculating ionization energy. So energy levels converge at high energies. This is review, but we have a term for this. When they converge at high energies, we call this the convergence limit. Call this the convergence limit. So what does that mean? Well, that's just this is where the electron is ionized. It's a bit of review from what we wrote before, but that's where we have moved the electron past the pole of the nucleus or the nuclear charge. The special thing about this is if the wavelength, lambda, we learned that from light, or the F frequency of the convergence limit is known, we can calculate the ionization energy. So basically what we're saying is if we have some atom, so we have some atom with an electron, let's just say there's an electron right here, and some light hits it, boom, and that electron leaves n equals infinity, and we'll say this is n equals 1. If that electron leaves, if we know either the wavelength or frequency of our light, we can determine the ionization energy. So how do we do this? Well, it's very simple. We use two formulas. The first formula we use is E equals hf, where E is the energy. That'll be measured in joules. H is a constant called Planck's constant. This is in your data booklet. It is 6.63 times 10 to the minus 34th joules seconds. And lastly, we have frequency. And this is just seconds to the minus 1. You'll notice that when we multiply our two values together, seconds will cancel with seconds, and we're left with joules, which matches joules. So even our units work out. That's called dimensional analysis, looking at the units to figure out whether or not it works. Our other equation is C equals lambda F. We covered this one a little earlier, but C is our speed of light. This is a constant as well. It's 3.0 times 10 to the 8th meters seconds to the negative 1. And then we have lambda, which is our wavelength of light, which is measured in meters. And we have, once again, F, our frequency, which is measured in seconds to the negative 1. And once again, dimensional analysis shows us that if we take seconds to the negative 1 times meters, we get meters to seconds to the negative 1, or meters per second, which is a speed. All right. So how do we actually use this to calculate ionization energy? The best way is to do some practice. So if you want to try and do these problems as I cover them, just pause the video, take a chance, and then play to see if you're right. So the first one is frequency of the convergence limit is given as 3.28 times 10 to the 15th seconds to the negative first power. The question is, what is the ionization energy in kilojoules? So you need to do a little bit of unit conversion, but we have to see a couple things. First, we are given two values. So if you want to try it now, pause now. So we're given frequency and we're asking for the energy. So if I go back to my equations, I see that I have two that deal with frequency. I have frequency and I have frequency. However, the first one also has energy. So I'm going to use this first equation because I have frequency, I have Planck's constant, I multiply them, I get energy. So let's go ahead and solve. Energy is equal to HF. I'm going to try and keep everything nice and neat so I don't get things confused. Energy is equal to 6.63 times 10 to the negative 34th joules seconds times 3.28 times 10 to the 15th seconds inverse. I notice my units seconds inverse cancels with seconds, and I can solve this to get energy is equal to 2.17 times 10 to the minus 18th joules. The final aspect of this is that my answer is asked for in kilojoules, not joules. So what I'm going to do is I'm just going to divide by 1,000. Or I'll change the color on that. Kilojoules. So we'll divide by 1,000, or you could just divide by 10 to the third, and you get energy equals 2.17 times 10 to the minus 21st kilojoules. A lot of times the IB will actually ask you for an answer in kilojoules. Kilojoules is very often used in chemistry as joules is too small unit of measurement for most of the things that we deal with. So unless you're in HL studying entropy, you're not really going to be using joules very much. All right, number 2. Determine the wavelength of a photon that will ionize copper. Or sorry, not ionize copper, ionize an atom of copper. So one atom of copper. We are given that the ionization energy of a copper atom is 1.24 times 10 to the minus 18th joules. So once again, if you want to solve it yourself, pause and then come back. But I'm going to get started. So I notice that I'm given the wavelength and I'm looking for the wavelength and I'm given the energy. So if I go up to my equations, well, I'm given the energy, so I must start with this equation. However, wavelength is in this equation. The combining unit is frequency. So what I'm going to do is I'm going to solve for frequency and then apply it to this equation. So this is the part where HL really is just a lot of algebra more than anything else. So you're going to have to get used to it a little bit. Energy equals HF. Therefore, because I'm looking for frequency, I will rearrange it so that frequency is equal to energy divided by H. Frequency is equal to 1.24 times 10 to the minus 18th joules. That will be divided by 6.63 times 10 to the minus 34th joules seconds. I'll notice that my joules will cancel out and I will be left with inverse seconds. Therefore, my frequency is 1.87 times 10 to the 15th seconds inverse. Wonderful. I have my frequency now, so I'm going to use my second equation. C equals lambda F. Oh, sorry. I was using nu, which is what I used to use for frequency, but that's more of a physics and a chemistry thing. And I'm going to rearrange it so that I have isolated lambda, just like I rearranged it to isolate frequency. Lambda is equal to C divided by F. Therefore, lambda is equal to 3.0 times 10 to the 8th meters seconds inverse, all divided by 1.87 times 10 to the 15th seconds inverse. I will notice that seconds inverse divided by seconds inverse cancel out, and I get my answer in meters, which is good because that's a unit I need. I get 1.60 times 10 to the negative 7 meters. And just like that, I have found the wavelength of the photon that ionizes a copper atom. So hopefully this helped you learn a little bit about ionization energies and have a great day.